Hi, the next step in proving the strong law of large numbers is proving two analytic lemmas. There is not going to be any probability involved, just analysis. The first of these is Toeplitz lemma. Toeplitz lemma. The assumptions are that we have some coefficients a, n that are non-negative, and b is the sum of the first n of these, which is of course non-negative as well. Actually what we need is that this is strictly positive, so we need this to be strictly positive for n at least 1, and we also assume that the bn goes to infinity as n goes to infinity. So the a is actually not summable. Let's now have a sequence. This is not random, it's just some real numbers, fixed real numbers. Let's now have a sequence xn that converges to x. The statement is that in this case 1 over bn sum from 1 through n of aj xj also converges to x as n goes to infinity. Alright? Before proving this, I'd like to show you a special case of this. Example, if you fix an to be 1 everywhere, then of course bn is the sum of 1s up to n, so that's n. That completely satisfies the assumptions we have. And then the right hand side, or the statement, becomes 1 over n sum of the xj converging to x, and the left hand side is called the Cesaro limit. Cesaro, actually the accent is that way. Cesaro limit of the x's. So a special case of Toeplitz lemma is saying that the Cesaro limit of convergent sequences is also converging to the same limit. But that's only a special case. Okay, to prove this, here is what we can do. So step 1 is, I'm going to do steps with different colors. Step 1, if I fix epsilon, then just by using the convergence of the axes, there exists a critical index n naught, so that whenever n is at least n naught, we have xn being closer to its limit than epsilon half. That's just convergence of the sequence x. Okay, once this is fixed, then the next observation is that there exists an n1 that I need to be larger than n naught, such that if I now do this quantity, j goes from 1 through n naught, and then aj, and then xj minus x, that's a fixed number. It depends on n naught, but otherwise it's just a number. Think about this as a fixed number. I can move the indices large enough, namely, I can move the indices up to n1. Since bn goes to infinity, n naught is fixed, I can pick n1 large enough so that dividing by bn1, this can be made arbitrarily small. I want to make it smaller than epsilon half. These are my two assumptions, observations actually. These are just direct consequences of convergence of xn to x and bn going to infinity. And with these tools, I can then look at the difference between 1 over bn, the sum, and x. So let's look at that difference. If I look at 1 over bn times, this is times, the sum j goes from 1 through n aj xj, and the difference of that to x, then one thing I can immediately notice is because the b is the sum of the a, I can easily rewrite x in terms of the just a fixed number x. I can easily write this into a similar sum than the other term. if I do the sum of the aj's up to n, that's exactly what I call Bn. And if I now multiply this with x, then I get x. So this is just a trivial rewriting of this number x just by the definition of Bn. And then this sum actually becomes 1 over Bn factor in front. The sum will have aj xj and aj x in it. The aj's are positive, and we have the triangle inequality for the sum, so I can bound my left hand side as the common positive factor 1 over Bn, the common sum in j, the common factor inside the sum aj, which is here in both sides, and with the triangle inequality and using that the aj's are non-negative, I can bring the mod inside the summation, making my new term larger than before. So that's the next step I'm doing, and I'm going to split this sum into two parts. So first let me just write 1 over b, and for the moment I'm going to put n here. I split this sum up to n naught, and then I proceed with the sum from n naught plus 1 up to infinity. No, actually, sorry, up to n only. And what I'm doing here is true for n, at least n naught. In fact, I'm going to do this for, you can't see this, I'm going to do this for n at least n1, and by assumption n1 is larger than n naught. So I'm doing all this for n at least n1. In that case, I can split the summation from 1 to n naught, and then n naught plus 1 to n. Okay, and aj, and then xj minus x. Okay, and so far it's actually equal. So far I could have an equality here. The reason I'm going to, the way I'm going to make it a bound is putting in an index n1 instead of n. n1 is smaller than n, so b of n1, b is an increasing sequence because the a's are positive. b of n1 is smaller than b of n, so this 1 over b of n1 is larger than 1 over b of n, and that's why this became an inequality in the good direction. And now what I want to do, now what I need to do is look at my two observations I had before. Observation 1 tells me that xn minus x is closer to each other than epsilon half whenever n is larger than n naught. So here j is larger than n naught, so xj minus x is closer to each other, xj minus x is smaller than epsilon half, and that's because of observation 1. For the other term, I have 1 over bn1, this sum up to a naught, aj xj minus x. So these were set up to make sure that this term here is less than epsilon half altogether. So I can continue my line with this epsilon half bound on the first term, smaller than or equal epsilon over 2 on the first term, plus 1 over bn, that's this term here, and then I have an epsilon over 2 for bounding each of the xj minus x's, and I have the sum from n naught plus 1 to n of the aj's. If it were from 1 through n, then it would exactly be bn. The bn was defined to be the sum of the ai's. Okay, so if this was to go from 1 through n, then that would be the Bn over here. It only goes from n naught plus 1, so I can actually subtract b of n naught. Doesn't really matter, this is positive, so if I forget about this term, I just make everything larger. Epsilon half. Forgetting this term leaves me with bn over bn, that's 1 times epsilon half, so that's epsilon. And what I achieved is that I started with fixing an epsilon, and I show that I can take large enough n's so that my difference between 1 over b and the sum of the ax's and x is smaller than epsilon, which exactly is what I wanted to conclude, that sum of the aj xj over bn actually concludes to x. So that finishes the proof of Toeplitz now.